Okay, good afternoon, everybody. Thanks for coming. This is a pretty small group, so if we've got questions or comments, let's take them along the way. This afternoon, I'm going to look at developments in diesel engine technologies and fuel supplies over the last couple of decades, and ways in which these are potentially mutually incompatible. We've had very rapid evolution of our fuel supplies and our engines, and some of these things are moving in opposite directions. And what, of course, is driving this is the emission standards. So if we take a look at these, the key things that we're testing for in emissions are nitrous oxides and particulate matter. And over the last decade or so, the standards have gotten tougher and tougher, particularly on the nitrous oxides, and particularly in the States, more so than in Europe. And then we have a separate set of standards which are testing basically for fuel efficiency by measuring carbon dioxide, because carbon dioxide is directly proportional to your fuel burn rate. So if you require car makers or whoever to get more miles per gram of carbon dioxide, then they have to improve fuel efficiency. That's the only way to do it. What has happened in the last round of emissions requirements is that in order to get the particulate matter and the nitrous oxides down, we've started to sacrifice fuel efficiency. So the two sets of standards have become mutually incompatible. And this, of course, is where Volkswagen got caught, because they had software. When you go in an emissions lab to test a car for your emissions, it's done at a standard barometric pressure and a standard temperature, so that everybody's the same. And then you put the car on a dyno and you spin the wheels, the drive wheels, and then you put a brake on the dyno and to put a load on the car, and then you measure the emissions at a given load. So Volkswagen software was set up such that if the barometric pressure was at a certain level and the temperature was at a certain level and only one set of wheels was spinning, then they were in the test chamber. And at that point, they basically flipped a digital switch and switched into emissions test mode. If they didn't see those three conditions, they knew they weren't in the test lab, so they flipped the switch the other way and they went into fuel optimization mode. In fuel optimization mode, the emissions were between 10 and 40 times over the allowable limit in the States. And this is what's gotten them into trouble. And effectively, what they were trying to do was to avoid putting expensive and bulky after exhaust treatment systems onto the cars to keep the emissions within bounds and also to maintain the efficiency. So that's what's going on with Volkswagen. So as I say, we've had this progressive reduction in emissions limits. It's been driven by the highway standards. What we have right now is that the highway standards are being phased into the marine world. In the States, this is EPA Tier 3, and in Europe, this is RCD 16, which starts to get implemented in January next year, and with full implementation by January 2017. The RCD 16 has got the same emissions limit as the EPA Tier 3. So both the US and Europe are going to be in sync at this point on emissions. And basically they have two engine sizes up to about 600 kilowatts. You've got one set of standards, and then above 600 kilowatts, you've got another set of standards. The emissions technology for above 600 kilowatts is explicitly called SCR forcing technology. That's selective catalytic reduction. It's designed to force engine manufacturers into a certain emissions technology, which is bulky and difficult to implement. So ICOMIA lobbied quite heavily with the IMO, which is the International Maritime Organization, to get these standards delayed. And in the recreational world, they've set that back another 5 years. So you can get away without having to comply with those standards for 5 more years in boats up to 500 gross tons for recreational use. But commercial users are going to have to comply with those standards by January of 2017. In order to meet these toughening emission standards, the engine manufacturers have gone through a number of technologies. We have exhaust gas recirculation, which is a technique for keeping down cylinder temperatures, because the higher the temperature, the more the nitrous oxides. We've got soot filters, basically, which are catalytic converters for diesel engines. And then for the bigger engines, we've got this selective catalytic reduction, which is when you inject urea into the exhaust stream, and it combines with the nitrous oxides at high temperature and turns it into nitrogen, which is a harmless gas. 80% of the air we breathe is nitrogen. So those are the technologies we've been driven into. And then the other thing they've gone into is very high pressure injection systems, because they can get much better control over the fuel burn process and reduce the emissions through that technique. And in particular, we've seen common rail systems, unit injection systems, and unit pump systems. But by far the most predominant technology is common rail injection systems. In these systems, you raise the injection pressures. Right, currently, we're looking at around 40,000 pounds per square inch. That's about 3,000 bar. I mean, quite staggering pressures. The prediction is over the next few years that we're going to go as high as 60,000 pounds per square inch on these systems, 4,000 bar. Unbelievable pressures. To get these kinds of pressures, you've got to have machining tolerances of millionths of a meter or an inch. We're talking 1 or 2, 3 microns, where a micron is a millionth of a meter. And when you've got these kind of machining tolerances, you cannot afford any kind of contamination of the fuel supply whatsoever. With a conventional mechanical injection system, which is running at about 5,000 pounds per square inch, whatever that is in bar, I can't remember, the most damaging particles are around 6 to 7 microns. So typically your secondary engine-mounted filter is around 7 microns. It might be lower, but if you get everything down to 7 microns, you're doing okay. When you get to these high-pressure injection systems, particularly the common rail, particles of 1 to 3 microns are the most damaging. What happens is you get a tiny little particle like that comes through the system, and if it gets trapped between the working surfaces in the injectors, it causes a tiny little dent in the metal surfaces. And then the next time around it gets flushed out, but over time you get a load of these dents, and if they get to where they line up, which they eventually will if there's enough of them, you then get a path for fluid to go down those dents, and at 40, 50, 60,000, 3 to 4,000 bar pressure, it's like a water jet cutter, and it cuts a groove in the injector seat, and then it destroys the injector. So we have to get rid of these particles down to 1 to 3 microns. To do that, you absolutely have to have a minimum of 2-stage filtration on all marine engines, which is to say you have to have a primary filter, which is mounted off the engine and which won't come from the engine manufacturer, which you've got to put in yourself, and then you have the secondary filter that's mounted on the engine. Within the filter world, up until fairly recently, the standard test for filter effectiveness only went down to 4 microns. All of the test equipment that's currently used by filter manufacturers goes down to 4 microns and no lower. In other words, they're not even counting the 1 to 3 micron particles that are the most damaging for these high pressure systems. They don't even have the equipment that can count down to that level. The filter manufacturers themselves have a set of tests that they have to test the filters to in order to give them their rating, their 2 micron, 3, 4, whatever it is, and also to give them an efficiency rating. They're testing with equipment that measures down to 4 microns, and they're using test dusts that have a mixture of particle sizes, most of which are in the 20 to 30 micron range. So the test dusts and the equipment that they're using are not suitable for the filtration levels that we need for these modern engines. And then I've got some numbers up there. Back as long ago as 1998, the engine manufacturers realized that this was going to be a problem, and they developed something called the Worldwide Fuel Charter, WWFC, and within that they defined certain fuel cleanliness levels that they wanted to see, targets for fuel delivery systems. And these are specified in terms of this ISO standard 4406, and it's a really weird way they count particles, but effectively they have 3 sizes they're counting: 4 microns, I think it's 7. What have I got up there? I forget. 6 and 14. And then the way they count them is through multiples of the number 2. And I won't get into the counting process, but you end up with a target cleanliness level of 18, 16, 13, which is specifying a number of particles at the different particle sizes. And that is the target for the Worldwide Fuel Charter, which incidentally hasn't changed since 1998, and they've been through 5 editions of that now and revisions. The last one was in 2013. So we're looking at 2,000 particles at the 4 micron level in the sample size, which is a milliliter, 500 at 6, and 60 particles at 14 microns. If you look at the target that the fuel injector manufacturers have got for common rail systems, it's 1296, which is 30 at 4 microns. So immediately we can see that at the 4 micron level, the target for the fuel injection systems is almost 100 times below the target for the fuel delivery system. On top of that, every time people do widespread analysis of fuel quality on the delivery side, they discover that typically the particle count is double what you've got for the target. So now we're looking at discrepancies of 1 to 2,000 times from the fuel delivery system to the target at the engine. And that all has to be removed by the fuel filtration system on the engine. We have got additional problems. The fuel testing procedures, which are specified in 2 ISO documents and then in similar SAE documents in the States, it's a multi-pass process, a multi-circulation process, a multi-pass through the filter, which is designed for hydraulic systems and not for engine delivery systems. They're using hydraulic fluid in most of these tests and not diesel fluid, so the viscosity is totally different. As I mentioned earlier, they're using particle counts that are not suitable for common rail engines. And on top of that, they're doing steady state measurements and not measuring for acceleration and deceleration. So there's a whole number of ways in which these tests absolutely do not reflect what's happening in the real world. It was interesting that last summer, the Sunday Times magazine, before the Volkswagen scandal broke, took 19 diesel engine cars out on the road and tested them, and they discovered that during acceleration and deceleration, the certain particle counts, the emissions counts, were typically 10 times above what they got in the steady state conditions they use in the lab. Well, it's similar with these fuel filters. When you accelerate and decelerate and you get vibration and so on, you get all of a sudden a whole slug of particles that get shaken loose and come through the filters. The typical premium filter medium at the moment is good down to a nominal 2 microns and is put in at 99.5% efficient. And you think 99.5% efficient, that's really, really efficient. We're only 0.5% away from absolute efficiency. But in practice, when you look at the way these engines operate in the real world and the way the fuel supply is being delivered from the marinas and other sources, you discover that what you need is a much more reliable 2 micron filter with an efficiency rating of 99.99%. They don't exist in the marketplace at the moment. You can get there with contemporary filters by putting a bunch of filters in series. On the top slides there, I've got filters in parallel, which many of you will see on boats. It enables you to switch between filters, so you can change one filter while the engine's still running. You switch to the other filter. But to get these very high filtration levels, you need filters in series where there's no valves in there. You're going through one filter and out of that and into the next one and so on. And you may need 2 or 3 2-micron filters in series to clean up the fuel supply to get it down to the levels that these high-pressure engines really are looking for. And then, of course, you've got a real problem because the filters plug up really fast when you've got that kind of small pore structure in the filter. We've got an additional problem is that once they started putting catalytic converters onto engines, you cannot have sulfur in the fuel supply because the sulfur messes up the catalytic converters. So concurrent with all of these toughening emission standards, they've removed the sulfur from the fuel supply. And 20 years ago, it was quite common to see 4% sulfur, 40,000 parts per million. Now the legal limit in the States is 15 parts per million, and in Europe it's 10. And that's called ultra-low sulfur diesel. Well, the process of taking the sulfur out of the diesel supply removes a lot of the lubricity, and that's important for the injection equipment. So then they add additives to it to put that back and some of the other properties. But one of the characteristics of these additives is that they increase the ability of the fuel to hold small particles of water. It doesn't settle out in the same way that it does with a standard petrodiesel with high sulfur in it. At the same time, we've been adding biodiesel to the fuel supply. I believe in Europe there's a 7% mandate, which actually is not being adhered to at the moment, but that's the target. Biodiesel also has this high surfactancy, it's called, where it breaks up the water into very small particles that can be held in the fuel supply. The current mechanisms for removing water from the fuel supply, which are either hydrophobic, where you have fibers that repel water and then the water beads up till it gets into large enough drops to fall to the bottom of the filter, or you've got hydrophilic media which attracts the water droplets and then again they build up till they're big enough to fall out. Well, neither of the current popular methods for getting water out of the fuel supply will get rid of this entrained water in the high surfactancy fuels. It goes right through these filters. And in fact, in the aircraft world, they ban high surfactancy fuels for precisely that reason, because you can't get the water out using conventional filtration techniques. So they have been looking at this at the standards side, and they've been tweaking the standards to where they've lowered the allowable water content going through, and they've also lowered what they call the interfacial tension standard, which is the extent to which the water will get broken up into these tiny droplets. But even so, the latest generation of the standards does not reflect fuels with high biofuel content. So we're going to find that even if a filter complies with the latest generation of water removal standards, it's still not going to get all of the water out of these the higher biofuel mixes. Another problem with biofuel is it's a solvent. And actually, I think my next slide is my own boat. I pulled up at a marina in Sweden where they'd just taken on biofuel, and I think probably for the first time. It dissolved all of the gunk out of the marina system, I think is what happened, and it completely fouled up the injection system or the fuel system on my boat the first time I tried to run it, because all of that crap came out of their fuel tank and into mine. So that's another issue with the biofuels. And then a really serious issue is they've got a very, very short shelf life. If you're using B20, which is 20% biodiesel, it's recommended that it get burned within 90 days from the time it's produced at the factory. So that includes all of its transportation time and storage within the marina. If you're using 100% biofuel, the recommendation is that you've got to use it within 45 days. And obviously within the marine world, we frequently have fuels that sit in tanks for years at a time. So that's going to be a bit of an issue, particularly with boats that get laid up. So that's the water bit. I got a little ahead of myself there, talking about the entrained water in the fuel supply. There are some dissolved water tests. You can send it away and get it done, but this is one I discovered recently. I haven't actually tested it myself, but I threw it up there because it looks interesting. For $10, you can buy a little kit where you can test for entrained water. And I think we're going to see more of these coming on the market, and we're going to need to use them, quite frankly. So the bottom line is that the diesel fuel that meets the current supply chain cleanliness requirements and other chemical requirements and so on, and filters that pass all of the relevant tests, actually are not good enough to protect modern injection systems. So we've got this mismatch between the fuel supply and the filtration industry and the engines that we're using today. This will go away in time. The next generation of automotive standards are going to require a significant toughening up in the automotive world. And in response to that, the engine manufacturers are going to demand of the filter manufacturers that they produce better filters. But it's going to take time. The first thing they're going to try and do is use the existing microfiber technology to get more efficient filters. And actually that doesn't work very well because the fibers can break up and come through and wreck the injection systems. We are beginning to see the first generation of different media, non-glass-based media, that have the required efficiency levels up to 99.99% and below the 4 micron level. But it's going to take several years before this stuff filters down into the marine world. And in the meantime, we're just going to have to be very, very careful. On the gasoline side, back in, how am I doing for time, Patrick? Okay. Back in 2005 and 2007, the Americans passed a couple of laws that had absolute numbers on the amount of renewable fuels that went in the fuel supply. So in other words, they didn't say that 5% or 10% of the fuel had to be at a certain level. They said by 2015 we had to be using 15 billion gallons, I think it was, of renewables. In the States, the only way to ramp up for this quickly was to use corn-based ethanol. So that's what we've got. And they pumped that into the gasoline supply, and up to a 10% mix, which is the E10, the ethanol was cheaper than gasoline in those days. Nowadays, the gasoline price has gone down, so it's about a wash. So it was no problem for everybody to meet the specs by just pumping more ethanol into the system. And then we get to E10. Once you go above 10% ethanol, the ethanol again is a solvent. It starts to screw up fuel systems, and it starts to screw up the delivery system. So there was a legal limit at E10. They hit the E10 threshold in about 2012, when initially they hadn't expected to get there till 2017, 2018. The reason being because the automobiles are more efficient in the States, so the gasoline consumption has gone down over what they expected, and because they had this absolute number, you've got to get to 15 billion gallons, they hit that threshold earlier than expected. So then there was a big argument in the States with the oil industry saying, you know, we need to lower the limit and make it just a percentage-based one. And the ethanol producers, which includes some of the biggest lobbying organizations, Monsanto, Archer, Midland, Daniels, and so on, saying, no, wait a minute, you always said this was the number, and we've spent billions of dollars gearing up for this. So that has not been resolved. It's going to be resolved this month. It's almost certain that they will basically raise the bar to where they've got to what they call break through the blend wall, the E10 blend wall, which means we're going to see higher ethanol blends in the States, and we're already seeing in a lot of the gas stations E15 on offer. The problem with ethanol in marine engines is that ethanol chemically adds oxygen to the system, which raises the exhaust temperatures and the burn temperatures. And on all automobiles, you have an oxygen sensor in the exhaust system, and if you see the oxygen levels going too high and the temperatures going too high, then you tweak the whole injection system to bring it down within bounds. On almost all of our old marine engines are open loop engines, which is to say they have no ability to react like this. And if you run these engines at wide open throttle on more than E10 ethanol, you're going to burn them up. And there were a bunch of tests done in the States by Mercury Marine, I think Volvo participated, and another engine manufacturer, with outboard motors using E15 gasoline, 15% ethanol. Not a single one of those engines got to the end of its warranty period at wide open throttle. And so I don't know what the blend levels are in Europe at the moment, but you've got a similar kind of pressure to put more renewables into the fuel supply. And if you start breaching that E10, 10% level with ethanol, there are other renewables that don't have this effect. Then you get into these problems with burning out the engines. Basically, it destroys the valves and the pistons through getting them too hot. There are other problems with ethanol. It has a much lower energy density than gasoline. It's only 67%. So the more ethanol you put in the system, the more fuel you've got to burn to get the same energy output. It absorbs water, and if the water content goes above a certain level, which in the marine atmosphere we have a lot of humidity, then the ethanol separates out. They call it phase separation, at which point if you pull that into your engine, you're going to wreck the engine. And even if you get rid of it, the remaining gasoline is not suitable to burn in the engine. Again, it's a solvent. On older engine, it'll dissolve rubber components. On engines that were on boats built up until the 1990s, with a lot of them have fiberglass fuel tanks in the States, the ethanol will dissolve the resin out of the tanks. And then the tanks just leak like a sieve. And it has, again, a reduced storage time. There are alternative renewables that don't have these negative side effects. One of them is called biobutanol. The testing done by Volvo Penta and the others, Mercruiser, demonstrated that you could put 16% biobutanol in the system without harming any marine engine. Since biobutanol is also more efficient than ethanol, 16% biobutanol has the same effect as 20% of ethanol. So by putting biobutanol in the fuel supply, you can effectively get to E20, in other words, a higher effective blend rate, without screwing up the engines. So there are moves afoot, particularly in the States, to start substituting biobutanol for ethanol. And in fact, we've got right now the first marinas operating on the east coast of the US. There's half a dozen of them will be in operation this coming year that are dispensing biobutanol from the fuel system. So, just to sum up, and incidentally, all of this is written in far more detail in Professional Boat Builder magazine. If any of you are not subscribers, the booth is over in the corner there. It's free for anybody that's in the trade. It's a fabulous magazine. So go and sign up and get the magazine. But to sum up, we're in a period of rapid change for both fuel supplies and engine technologies, and there's no signs of this slowing down. Some of these changes are hazardous to older engines, particularly the ethanol blends. Some of these changes are hazardous to our newer engine technologies, and particularly the high-pressure injection systems. For the foreseeable future, we're going to have to be really careful in terms of monitoring the fuel supply, taking extra precautions with the high-pressure engines to make sure that we're getting clean fuel at the injectors, and basically just monitoring this situation until the standards writing bodies get on top of this, which is going to take several years, and basically force the fuel suppliers and the filter manufacturers to clean up the system for us. At the moment, when you buy an engine, the warranty specifically excludes damage from inappropriate fuel. So the engine manufacturers have shifted the burden onto you and onto the engine owner in a situation in which we don't have adequate protection for the engines. So we've got to be very, very careful over the next few years in how we deal with the fuel supply and clean it up.